Let's continue with acid-base indicators. Acid-base indicators, known also as pH indicators, are chemical species that change color with pH. This is a representation of what happened with the indicator when such indicator is present in acidic or basic solution. Usually indicators are organic molecules, like for example, this one. I believe this represents phenolphthalein and has acidic form. Look, this OH here attached to this oxygen here. This bond here, oxygen hydrogen, is weak. This behaves, this is an OH group for the phenolic function in organic chemistry. But phenols behave as a weak, very weak acids, because this bond here between oxygen and hydrogen is very weak. So this can be ionized. Similar here. So we can say that this molecule has two acidic hydrogens. In other words, these molecules can donate those hydrogens in aqueous solution. So we had two forms of the substance of this molecule. One, which is the acidic. We have that representation here. H represents for the acidic hydrogen, and this is this can be represent any indicator in aqueous solution. So let's say this compound has one color when it's in the acidic form. For the case of phenolphthalein, it is colorless. Forms colorless, clear colorless solutions. When the hydrogen is transferred to the water, so the water is accepting that proton, the molecule gains a negative charge. And it shows the basic form. So here, the hydrogen is transferred to the water to form the hydrogen ion and the basic form of the molecule, which is the conjugate base. And that will show a different color. So the difference between these two species, the acid and its conjugate base, again, is just one hydrogen. And that makes a big difference in the color. So this type of substances that behave this way are really important in wet chemistry, because they help us to figure if a solution is acid or base when we observe the color change on the indicator. So let's see some of those indicators and what are the color changes. We also have a number of natural acid-base indicators. Let's check this. Beet juice are also very good to make natural acid-base indicators. Look the color of the beet juice when they are in a different pH. So you change the pH of the juice by adding a weak acid or a weak base to that, you will see color changes from red to violet. And the change occurs around here, around 6 point, starts to occur around 6.5. Blueberries, you see different colors here. They chose a green color here. I'm talking about the blueberry juice. So the blueberry juice contains chemicals that behave like acid-base indicators. And all of these naturally occurring substances, especially some fruits and vegetable juices containing those substances that behave as acid-base indicator, they change color in a different pHs. So just by looking at the color, you know what character is in the solution. If you have a basic solution or you have a acidic solution. The most common, probably easy to make at home. Your kitchen is, as I mentioned it before, is the red cabbage. You take the juice, you boil few leaves of red cabbage in water, you extract the juice, probably the juice has this color, right? But it's a mixture, it's not just one molecule presenting all different colors. It's a mixture of different chemical compounds that behave as acid-base indicators. You can use those drops of those, few drops of this juice to a, for example, lemon juice, and you will see it will turn, the indicator will turn towards these gamma colors here. If you add the red cabbage juice into milk, milk is usually slightly basic, so you will see the color of the cabbage juice going towards this color, towards blue, and here in this case like a greenish. And those are natural occurring indicators. Here, most commonly used acid-base indicators in the chemistry lab, we have the universal indicator. It shows a gamma of color changes from 0 pH to 14 pH. Again, the universal indicator can make those color changes because it's a mixture of different indicators, every indicator changing at different pHs. So this is very useful acid-base indicators. More narrow change is this one. This is pure one. This is not a mixture, it's phenolphthalein. And that changes around 8.2, 8.3 from colorless to pink when the pH is 8.2 and above. Below 8.3, below pH 8.3, this indicator has no color, so it's clear colorless in aqueous solution. So very important to remember that. The phenolphthalein doesn't tell you if the solution is acidic or neutral. It could be neutral and still colorless. And still, it could be a little bit basic and still colorless. It changes to a pink color when it reaches 8.3. But very used indicator in the chemistry lab. The metal orange also changes from red to yellow, and the range of change is between 3.1 and 4.4. When that change occurs somewhere here, it's going to show during that transition both colors to our eyes, the red and the yellow. So probably you will see like a greenish somewhere here, because during that transition you have some molecules still in the acidic form and some molecules of the metal orange already in the basic form. So you have a mixture of the two colors, and you may see a color transition there, which is going to be different, no red, no yellow, somewhere in between. So what color would you get when you mix red and yellow? That's what you see here. For Timor blue, we have 3 different color changes here. The range goes between 1.2, somewhere here, from red to yellow. So the range goes from 1.2 to 0.8, and from 8 to 9.6. Here goes from yellow to blue. So this Timor blue goes through 2 different color change ranges, from red to yellow and from yellow to blue. Have another list of acid-base indicators. Again, very common use in the chemistry lab. These are very used in chemistry lab. Bromothymol blue, the limus. We have red limus solution. If that's acidic, it's going to be red. If you add some base to that limus solution, so you have the blue solution. Similar, you can have a red limus paper or blue limus paper. The red limus paper helps to identify bases. So remember, bases turn red limus paper blue, and acids turn red, blue limus paper, or better say, bases turn blue limus paper red, and so on and so forth. All these are very used. Here is about the color changes happening and the ranges. It's important to know the range where the indicator is changing. So it's not enough to say, for example, a solution changed to blue color to know what is the acid-base character of the solution. Because as you can see, different indicators turn blue color at different ranges. For example, this one, metal violet, turns blue at between 0.01 and 1.6, and still acidic, still acid. However, Timor blue turns blue color in a range between 8.98 to 9.6. And it's going to be that blue color will show basic for Timor blue. Whereas this blue color here will still show acidic if we are using metal blue. So you need to know what indicator you're using to figure what is the meaning of the color that indicator is giving. How? Just by looking the pH range for that color change. So usually what you have to ask is what indicator you are using, right? You see the indicator changed to red in solution A. That's giving no information at all there. You need to ask, okay, yes, turn red, but what indicator was that? Because look, in this chart list, there are probably more than 50 different indicators. And in this chart list, I'm showing only a few of them. But in this chart list, 4 indicators change color to red, right? From this case, from yellow to red, from yellow to red, from blue, from yellow to red, and from blue to red. And they change the color at different pH. All right, let's classify acids and bases as strong and weak. We can have strong acids or weak acids. We can have strong bases or weak bases. So what in chemistry, what is the meaning of that word, strong? What is the criteria we use to define the strength of the acid or base? It's very simple. And we follow only this criteria. And has to be with the ionization of the acid or base. Here are some examples of strong acids. The most used strong acid. So what is a strong acid? Strong acid is the acid that ionizes completely in a aqueous solution. That's it. That's strong. Complete ionization of the acid. And here we need to make difference between ionization and dissociation. Two words that sometimes they are exchangeable, but we need to be careful depending on what we're talking about. Let's take the example of hydrochloric acid. Again, hydrochloric acid, as I mentioned before, HCl. Let's assume this gas is already dissolved in water, and so we have aqueous already. Aqueous. We dissolve the gas in water, so we have aqueous hydrochloric acid. This is a neutral molecule. It is a molecule. That bond between hydrogen and chlorine is a covalent bond. So we have hydrogen sharing its only electron with chlorine. I'm using that structure to represent the process there. So chlorine has 7 valence electrons. If we do for chlorine, the atomic number is 17. We have the electron distribution as 1s2. 2s2, 2p6, 3s2, 3p5. So we have 17 electrons there. So we have 10 here and 7 here, 17 electrons. So on the outermost shell, we have 3s orbital and 3p orbital. That's for px, pc, and py orbitals. Here on 3s, chlorine has 2 electrons, and on 3p has 5 electrons. Remember the Hans rule: 1, 2, 3, 4, 5. So we have to apply the Hans rule, Pauli exclusion principle to fill these orbitals here. And for hydrogen, hydrogen 1 just has 1 S1 in this orbital. This is 1 S1, 1 electron. So you see that chlorine needs only 1 electron to fulfill the octet rule, to become, to look like the nearest noble gas, which is neon. Whereas hydrogen wants to look like the nearest noble gas, and this is the exception for the octet rule, helium, right? So we have here, and due to the difference of electronegativity of hydrogen is 2.1, and the electronegativity of chlorine is, I believe, 3.0, 3.5. All right, probably 3.0. I'm not sure about it. I have to check on the table. And we can check it now. So I got the confirmation from the periodic table. Electronegativity of chlorine is 3.0 using the Linus-Pauling scale. So that indicates two things. We have a covalent bond. These two species, these two atoms share these 2 electrons, and here the electron comes here, the orbital, and they share this pair of electrons, forming the bond. Also, that gives, due to the difference of electronegativity, a formation of dipole moment here, positive and negative. Also making this bond weak, because this pair of electrons are closer to chlorine nucleus. So we have a covalent bond. This is a molecule, it's neutral, and when that reacts with water, and water also has its own properties, having the structure, the shape and structure, and the electronegativity of oxygen, making a very polar substance here. So we have 2 dipoles, positive, and 1 dipole negative here, same thing here. So the electronic cloud is near to the oxygen, forming the strong negative dipole here, because remember this is a symmetrical molecule. It's not flat. Well, these three bonds are flat, but we need to take into account also the fact that pointing out of the plane, we have two non-bonding electrons, and behind this plane where I'm writing, we have another pair of non-bonding electrons. So these pair of electrons are here right in front, outside the plane, towards there with that angle, and this is behind. So that gives special properties. It's polar, very polar. Water is very polar molecule. And these two electrons are very anxious to get protons, or better, protons really wants these two electrons and feel like his noble gas, helium. All right, so water has, these properties of water plays a important factor during these acid-base reactions. So again, we have two neutral molecules holding covalent bonds. So they are, we cannot say those are ionic. We don't have ions here. We don't have ions here. However, due to this acid-base interaction, these molecules ionizes to form the hydrogen ion and chloride ion. So that's ionization. That's an ionization reaction. Other situation is when we have already ionic species. For example, we can say sodium chloride. Sodium chloride is already a ionic substance, right? It's a salt. This is a salt. Let me build a wall here. So we're talking about salts. Salts comes from the reaction of acid and base. And when we write the formulas for salts, usually what we have is a cation and an anion, and we write the formula in that order. We write, this is then an anion. Okay. Yeah. So we want to have negative charge there. This one will represent the cation, and this represents the anion. That's what we call a salt. So this is already a ionic species here. And when we have the ionic species in dissolved water in aqueous solution, it breaks down into its ions, again with the help of water plus Cl minus aqueous. With the help of water, it's water that helps to solvate this crystalline structure, dissolving its own into its own ions. In this case, when we already have a ionic species here, because this is the cation, this is the anion. In this case, we're talking about dissociation. So what is dissociation? To break down. Okay, so the sodium chloride dissociates into its ions, Na plus and Cl minus, and the hydrochloric acid ionizes into hydrogen ion and chloride ion. So be careful when we use these two words, ionization and dissociation. Strong acids ionize 100%, completely. 100% ionization for a strong acid, or complete ionization. That means that if you put a number of moles of hydrochloric acid into water, all of them, all your HCl molecules will ionize into these two species here, hydrogen ion and chloride ion. The conjugate acid and the conjugate base. Of course, if you have enough water. Let's assume we have enough water. If you add 10 molecules of this into water, all of them ionizes. So that means after you add your 10 molecules of HCl into water, you will only see this and that. You will not find HCl as molecules together. No, you won't find this anymore. Once you add this into water, all of them will ionize to make this. And if you try a few seconds later, oh, let me find one HCl molecule, you won't find it because all of them ionize. And that is what we call strong acid. And all of this behaves in the same way. They are strong acids because they ionize 100%. This is a complete ionization. So that's very clear definition of a strong acid. And that's why when we see here this arrow, you see this arrow is going in only one direction because it goes to completion all the way down. So the equilibrium shifts totally to the right, to the point that there's no need to talk about equilibrium. There's no equilibrium constant here. Well, we can actually measure it, but that equilibrium is too small. That number has a order of magnitude of negative, very high number. Negative high number, that means the number is very small. That's exponent. So there's no point to talk about equilibrium constant for a strong acids or bases. It's exactly the same definition for bases. So we have a list of important strong acids and strong bases. For strong bases, also they ionize completely. So from now on, when we talk about strong acids or strong bases, you don't need to look for the equilibrium constant because the equilibrium is totally shifted to the right. It goes to the completion. And you won't find, once you dissolve those in water, you won't find this species anymore. So what is a weak base or weak acid? This is important to know since the strong acids ionize completely. That means the concentration of H plus is exactly the same as initial concentration of the acid. This is important to know when you're solving problems. First, you need to recognize if your acid in your problem is strong or weak. Let's see this one. Let's practice with these problems. It says, calculate the pH of an aqueous solution at 25 degrees Celsius for the following concentrations. The first one is hydroiodic acid. First, we need to write the equation for every process. So hydroiodic acid, HI, you will write that, it's a little bit twisted there. Okay. Hydroiodic acid. When we say hydroiodic acid, right away it's telling you it's aqueous. If in a equation you see hydrogen plus I2 to form HI. Look, do you see water somewhere here? It's telling you about water? No. Probably you will find gas, and consequently, this is gas for most of the times. You see? So what is the name of this? This is hydrogen iodide. Hydrogen iodide, because it's a gas. It's molecular. Whereas here, when we say hydroiodic acid, now it's telling you it's dissolving water. That means you put the gas, you form the gas, conduct the gas using a pipes, put the pipe inside the water container with water, and you bubble this gas into the water, and the gas dissolves in the water, forming this hydroiodic gas. Probably here, this one doesn't behave as acid because it's non-water solution. Remember, it's water that helps to the process of ionization because of the polarity and the structure of water. So this one plus water, because it's aqueous, will ionize completely, since this was in the list of strong acids. We need to identify, we need to make sure if this is weak or strong. So yes, this is in the list of strong acids. So that means we have complete ionization here to form H3O+, plus I minus, and everything here is aqueous. And the problem is, what is the pH of the solution, of that solution? Notice that that is independent of the volume. You don't care about how much is there. The problem cannot, you have 1 liter of that solution with that concentration. What is important here? The concentration, because the concentration gives you the ratio moles per units of volume per liter. So it doesn't matter how much you have. You have 50 mLs of that solution, 0.035 molar HI. That's exactly the same pH as you have 500 liters of 0.035 molar HI. It's the concentration what you want to take care of. So the initial concentration of that, we write it here. Remember, we always write the initials 0.035, and make sure you have molarity, units of molar concentration. Since we said this dissociates completely, this one dissociates completely, then what is the final concentration of H3O plus? We have here 0.35 moles per liter. 0.035 moles per liter of HCl will bring, or will give up, or give off 0.035 moles per liter of hydrogen ions, 0.035. Molar. It's the same concentration, but you have to be careful in the molar ratio. The molar ratio, right? 1 mole of this gives 1 mole of that. You can write it this way also, it's acceptable. aqueous, breaking down into H plus and I minus, aqueous. So you see, now you see it clear. Here is the water. So don't let water trick you, because the concentration of water is constant there. What is changing is the concentration of HI. Therefore, the concentration of H plus from HI and the concentration of I minus from HI. So here is 0.035 molar of that, giving exactly the same number of moles per liter of H plus, 0.035 molar of that, in a 1-to-1 ratio or stoichiometry, because this molecule gives off only 1 mole. So you have to be careful on the stoichiometry and the type of acid you have. Some, we'll see later, acids, some can be monoprotic, diprotic, or polyprotic. That means one acid can sometimes give off 2 protons or even 3 protons. So you have to be careful with that. Once we know the concentration of H plus, concentration of hydrogen ions, it's easy to find the pH. If we apply the formula, pH equals negative log of concentration of H plus, so it's going to be negative log of 0.035. You can write it using scientific notation. You say negative log of 3.5 times 10 to the negative 2. And we know when you see this exponent, you know about in what range you are going to get the pH. All right. So what is your prediction? We'll see. So similar treatment you do for everyone, because all of these are considered strong acids. So here is the first one, you get pH 1.46 for the first one. For the second one, for the nitric acid, HNO3, which is strong, and this is the initial concentration of nitric acid, the pH of the solution will be the negative log of the concentration of H plus, which is exactly the same initial, because remember, we have a strong ionization, complete ionization for the strong acid. So the pH, when you plug this into the formula of pH, it's going to be negative log of 1.2 times 10 to the negative 4. And look the exponent, minus 4, negative 4. So you know that you can make some educated prediction here, and you will know that the range of the pH you are looking for. For the first one, remember this was 3.5 times 10 to the negative 2, and look the pH between 1 and 2. Here we have the exponent is 10 to the negative 3. So the pH, when you apply the log of the whole number, look the pH between 3 and 4. Here, the exponent is negative 5, so you know what is the range of pH. It's important that you think about these little details and make some educated predictions, because that way you will know if your results, whatever you get in your calculator or your calculations, are in the right direction. If for some reason you do this operation and you get a real weird number, like a 10.5, you know something is wrong, because you know having this, taking the negative log of a number with this exponent will not give you 10. All right, so this is how you do the analysis. The opposite to that, when the pH is given, you can find the concentration of H plus of hydrogen ion. So we apply the formula we just learned on the previous video. So let's say, and this is important to take, to do the analysis here. Let's say we have hydrochloric acid again, which is a strong acid. And we have HCl aqueous forming H3O plus aqueous plus Cl minus aqueous. Since this is a strong acid and we know the pH of the solution is 4.95, we want to know what is the concentration of H3O plus. So we go the opposite. What is the formula? The one we just we learned on the previous video. Concentration of H3O plus equals 10 to the negative pH. So the concentration for the first one, concentration of H3O plus is going to be 10 to the okay, 10 to the negative 95. right? So concentration of H3O plus equals 10 to the negative, this is the formula, 10 to the negative pH. And what is the pH? 4.95. 4.95. And since this was a strong acid, so you know the initial concentration of the strong acid is that too, right? That's what you put at the beginning to dissolve water. So that's how we solve this type of problems. And we round that off. You can round that off. This is about 1 times 10 to the negative 5, right? For the concentration. When you plug that in your calculator, you get the numbers. For bases, similar situation, we apply exactly the same definition of strength. For strong acids here, this is the list of group 1 in the periodic table, hydroxides. They are the hydroxides of group 1 metals. All of them are strong, all of them. Complete ionization, as you can see here. And for group 2, 2A, those are strong. They hardly dissolve in water. Some of them, magnesium, for example, barium, they doesn't dissolve well in water. However, the portion that dissolves ionizes completely. So that's another factor we are going to consider in the next chapter, which is the solubility and how that affects the pH. Okay, so calculations with the bases, similar. Let me give you an example of how you calculate the pH of a base. So we're talking about strong bases. That means they ionize completely in water. Let me do the first one, lithium hydroxide. For lithium hydroxide, let's choose red. Lithium gives a beautiful red color on a flame. All right. Like reddish. It's not exactly red, but it's in that range. So we write the equation for the ionization. We have lithium hydroxide aqueous that ionizes completely into lithium plus ions. Remember, ions exist for our purposes. Ions exist in the aqueous solutions. So let's start with the idea. When you have ion, you need to think in that's happening in aqueous. Of course, we can have ions in our gas phase, but that's different. So different processes. In here, in the wet chemistry that we're talking about, everything dissolved in water, ions are formed in the aqueous solutions, and they ionize because the presence of water. Plus or OH minus ion aqueous. Remember, OH minus, the hydroxide ion, is the most basic species. Whenever you see this species in water, you say, oh, it has to be basic. It's very strong. I mean, it's a very basic species. gives a very basic character to solutions containing the ion. All right, so the initial concentration is 0.013 molar, and since this is a strong base, ionizes completely. Therefore, once ionized, you will get 0.013 molar of OH minus. Therefore, we can calculate not the pH, but the POH, because we don't have hydrogen ions here. So we cannot calculate pH here directly. Instead, we have OH minus. So we can calculate what? POH. That's why we learned the application of negative log of X equals PX. In this case, negative log of OH equals POH. POH is the negative log of concentration of OH minus to find the POH. So let's find the POH. POH of that is negative log of 0.013. Again, this is going to be 1.3 times 10 to negative 2. So you know that that number is going to be small, between 1 and 2. You plug down in your calculator and you get, let me see, 1.89. That's the POH of the solution. Most of the times, we are really not interested in knowing the POH of basic solutions, of any solution. We need to focus more in the, because we don't have POH scale per se. Instead, we have a pH scale, everything based in the concentration of H plus. But since we know the relationship according with the KW, constant dissociation of water, KW, which is concentration of H plus, H3O plus times concentration of OH minus equals KW, which is a constant 1.0 times 10 to the negative 14. And remember, everything is just, for acids and bases, everything is just a balance between the concentration of these two species, the acid, the hydrogen ion, and the base. So one goes up, the other one goes down. And we can figure from here, what is the concentration? There are two ways to do it. From here, you can plug this concentration here and find what is the concentration of H3 plus. If the question was, what is the pH? But the initial question is, what is the pH? We found the POH. I'm just extending to another question. What is the pH? That's what we really want to know, the pH of solutions. So for bases, the first thing you need to do is to find the POH, and then from the POH, find what is the pH. How? Because from here, remember, we took negative log on both sides. We found that pH plus POH equals 14. Two important equations, equation 1 and equation 2. Which one do you want to use? to find pH. You can use either one to find pH. One is a long way and the other one is short way. Since we already walk up to here to find the pH, we just can plug that pH number here and find the pH. So pH equals 14 minus 1.89. And that is 12. 12. So here we have 11. 12.11. That will be the pH for the solution. That makes sense because when we look at the pH scale, bases have pH about 7. And since this is a strong base, the pH should be close to 14. So that's how you treat the bases, strong bases. That's how you find the pH for bases. And the other way will be if the concentration, initial concentration is given, therefore that's the concentration of OH minus. You can plug this concentration directly here to find the concentration of the H3O plus. Once you know the concentration of H3O plus, then you can find the pH. But since the problem was asking for the pOH first, then I just added an extra question, what was the pH? And that's how you do it. This one, for the barium hydroxide, we have to be careful because 1 mole of barium hydroxide, BaOH2, ionizes, giving off 2 OH minus. So 1 mole of this forms 2 moles of OH minus. So we have to take that into consideration. For example, we know the initial concentration of the barium hydroxide, which is 0.013, exactly the same, right? 0.013 moles per liter for the base. Zero point zero 0.013 molar. So 0.013 molar of barium hydroxide ionizes, giving 0.013 of barium 2 plus, and we don't care about that. And also giving 2 times that moles per liter of sodium hydroxide. So that's going to be 2 times 0.013 equals 0.026 molar. So you have to be careful with the stoichiometry. You see here, 1 mole gives 2 moles. So you have to take that into account. Now, you can find the pOH from here, because this is concentration of OH minus. You cannot find pH from here. You find only pOH, because that's what you have. And that will be here 1.59. You see these two hydroxides? with the same concentration, but this one, the stoichiometry is different. So pay attention to that. I leave this for you to do the analysis, critical thinking. If you solve it, post it on the Blackboard discussion. So we can start a discussion there about how to solve this problem. I would like to see your inputs. It's very important that you participate on our discussions. So be an active member of this course, not just a spectator. All right. It's here. Try yourself. Don't cheat. The solution is here. Try yourself first, and then post it. And you can compare your results with my results here. What about weak acids and weak bases? What is that? What is the definition? If a strong acid or a strong base are the ones that ionizes completely in aqueous solutions or have 100% ionization in aqueous solution. So what will be the definition of weak acids? Yes. So a weak acid is the acid that ionizes partially, that have a incomplete ionization in water. These weak acids and weak bases needs to be treated in a different way when we try to find the pH. Also, when we talk about weak acids and weak bases, we need to talk about equilibrium, because they establish the equilibrium. So therefore, for acids, we have the equilibrium of the weak acid, which is the Ka. And if we're talking about the base, we're talking about the equilibrium of the weak base, which is Kb, or equilibrium of the base dissociation, or ionization, better. This is one example.